Okay, so this is section 15.6. We're going to be talking about surface area. Now, considering the fact that we are talking about surface area in 3 dimensions, our surfaces are not going to be something which is just a nice, easy, smooth, clear, well, it's going to be a smooth surface, but it's not going to be just a flat surface. That would be something done in 2 dimensions. A couple of the surfaces might be flat surfaces, but some of them might not be. So in order to kind of talk about surface area and the concept here, we're going to go back to our idea in BC of arc length. Now, we did this formula last year or whenever you took BC, and if you had me before, I said that this is going to be one of those formulas I'm actually not going to prove, and I would save that for Calc 3. Well, here it is. So this is going to be the proof of the arc length formula that we came up with in BC Calculus. And the arc length formula was the integral of the square root of 1 plus the derivative f prime of x squared dx. And then obviously you throw bounds in there if you've got specific bounds that you're going to find the arc length over. The real question was why, because I never proved that. So let's go ahead and show the proof of this. All right, so we're going to have our curve, whatever it is specifically that our curve looks like. And just for the sake of doing this problem, I'm just going to make a curve that kind of looks like that. If I wanted to find the length of one segment of this curve, let's just say, so maybe from, well, if we want to do the entire curve, one way or the other, the idea was we're going to break these things into smaller segments. If we break these things into smaller segments, what I'm looking for is I can find the length of that particular piece, because that's literally just the length between 2 points, right? And that's a straight line. If I were to bring those 2 red dots smaller and closer together, that's going to end up giving us a really, really close approximation to the curve itself. And then if I were to add up all of those little arc lengths, all those little pieces, that's what's going to give us the length of the curve. Well, how do we actually find this, that blue dotted line? Well, there is going to be some kind of a vertical change. We're going to call that the change of y. And there's also going to be some kind of a horizontal change. We're going to call that the change of x. And then the idea was, again, if we were to make this distance right here very small. Now, it doesn't look like it based upon my drawing here, but I'm doing the drawing bigger so that you can kind of see. If we were to make that distance very small, what I would have to do is I would have to take the limit of the sum of all of the line segments that I could create along this entire arc. And that would be as n, excuse me, that's not supposed to be an equal sign, as n goes to infinity, I equals 1 to n. So you're basically saying, okay, I'm going to let the part in red, part in blue there be like that line segment, but then you'd have another line segment and another line segment and another line segment over here and then one over here, and you would let that become an infinite number of them. If you add up all of those things right there, that will give you the length of the arc. So if we want to find the length of just one of those segments, we'll call it L for now, we can find it by using Pythagorean theorem, right? Because that's basically the hypotenuse of that right triangle. So we would have delta y squared plus delta x squared, and then you would have to take the square root to get the length of that particular line segment. One other thing that we should agree on is that f prime of x, which is really it's the slope, so the slope is the change of y over the change of x, and that's going to be the case for very small delta y's. So for delta y being very small. So if I wanted to solve that equation for delta y, I would just multiply delta x on both sides, and you would ultimately get that delta y equals f prime of x delta x. So I'm going to go ahead and plug those into my line segment formula. So the line segment is going to be the square root of, excuse me, delta x squared, I am just changing the order, plus, and instead of the delta y, I'm going to replace that with f prime of x delta x and square it. So let's go ahead and distribute that square. Whoops. So we're going to have delta x squared plus f prime of x squared delta x squared, and that's just distributing the square. Well, I've got a delta x squared in common. I can factor out underneath my square root here delta x squared, which would then leave me with 1 plus f prime of x squared. And then I can actually take the square root of delta x squared out. So I'm going to have delta x times the square root of 1 plus f prime of x squared. So this represents the length of one segment. If I want to find the length of the entire thing of all the segments, I need to add them up. And if I let delta x become extremely small, or let all those line segments get very, very small, delta x becomes dx. So adding them all up, what I get is the integral of square root of 1 plus f prime of x squared dx. And that's the arc length in 2 dimensions. So how and or why does that have anything to do with surface area? So let's go ahead and take a look at this in 3 dimensions. All right, so what we've got is we've got this surface, which you can see there, and obviously the surface is curved over some kind of a domain. And our domain looks like it's got some kind of a square domain or maybe a rectangular domain in the xy plane. The projection of this patch right here, which is defined right there, the projection of that patch down into the xy plane also looks like it is rectangular. The interesting thing about this, though, is that the patch that we've got up there might not be rectangular on the surface itself. And that's because the surface is curving one way or the other. Obviously, if this was just a flat plane, the patch would be a perfect rectangle. Of course, if it was a flat plane, it would be much easier to take the surface area of anyway. But since this thing is curving, it's actually not going to necessarily form a rectangle. What it's going to form is a parallelogram. So a couple things we want to make sure. First of all, obviously this patch looks huge for our particular drawing here. But again, that's more for effect that you can see it than anything else. So these patches are going to be infinitely small. And what these patches are actually going to be that we're taking are going to be tangent planes. So we are going to actually be finding infinitely small tangent planes. Just like we did in 2 dimensions, we found infinitely small line segments. We're going to find infinitely small tangent planes to this curve. And to do that, we are going to have to double integrate the area of these patches. And the reason that we have to double integrate them is because you're going to have a tangent plane here, you're going to have a tangent plane here, tangent plane here. You're going to have tangent planes all along the surface in one direction. Well, you'll have to add up all those tangent planes, and then when you do that, you're going to have rows of tangent planes all the way across this thing. So then you're going to have to add up all those rows. So the first part of the integral will be actually integrating the areas of the tangent planes, and then the second one is going to be adding up all of the rows of the integrals, all of the rows of the tangent planes, excuse me. But again, the big piece of information here is that the area of these patches, these are all parallelograms. And that's because the angles in between what would be basically the two vectors that you could create from one corner of that patch may not necessarily be 90 degrees. Well, the good news is we have a nice formula to find the area of parallelograms if we can create two vectors from the same point. And we do have that. We're going to call this one right here, let's go with green since that's what I started. We're going to call that one vector A. We're going to call this one vector B. Well, if I want to find the area of a parallelogram, you have to do the magnitude of A cross B. And that will give you the area of a parallelogram. So, if I wanted to find the surface area of this entire thing, I'm going to have to take the double integral over my domain, which is the projection down into the xy plane, of the magnitude of A cross B. So basically, I'm going to take all of these A cross B's, and just kind of blew this thing up here so you could see it without the actual surface. Here's A, here's B. And again, the angle between A and B may not be a right angle. So from that perspective, we just don't know. Okay, so let's talk about a couple of things, because in order for us to do the magnitude of A cross B, really what we need is some kind of way of defining vector A and vector B. All right, so I'm going to kind of give you what vector A and vector B are, and then I'm going to explain how we actually arrived to this. So vector A is going to be defined by delta x, 0, f sub x, delta x. Vector B is going to be defined by 0, delta y, f sub y, delta y. All right, so now let's take a look at, excuse me, let's take a look at this diagram over here, see if we can't piece together why this is. So you can see over here, this is delta x, and you can see down here, that's delta y, and that should make sense. It's the change of x and the change of the y direction. But look at the change of z. You should be able to tell by looking at that this thing is slanted. It's not perfectly horizontal. It's not going to be parallel to the xy plane in most cases. Some of them might, but most of them won't. So to find the change of z, in this case, you're going to have to basically think about the partial derivatives. How are these things changing? Well, let's see. We know that the derivative, the partial derivative with respect to x is the same thing as the change of z over the change of x. So if I want to find the delta z, the change of z, I'm just simply going to multiply both sides of that by delta x. So we'll get that change of z equals the partial of x, delta x. Hopefully you can see that's what we have right here. That is our change of z. And if it didn't make sense already, I probably should have explained this up front. We're talking about vector A here first. Vector A has a change in the x direction. You should be able to see that. There's no change in the y direction because that vector is going to be it's going to be completely perpendicular to the y-axis. So there's no change in the y direction, but there is a change in the x direction. Likewise, vector B, we're going to create that one so that it has no change in the x direction right there because it's going to be perpendicular to the x-axis. It's going to have some kind of a change of y, and then it will have some kind of a change of z. Likewise, in order to find that change of z based upon the y part or based upon the b vector, we know that the partial of y is the change of z over the change of y. So solving that for the change of z, and again, it has to do with our b vector, change of z, multiplying both sides by delta y will be f sub y delta y. Now we have enough information, and hopefully that makes sense as far as where we got this from. Now we have enough information that we've got A, we've got B, we can perform the cross product. So let's do that. I think I'm going to try and squeeze this in over here on the right side. So we're going to do A cross B. Okay, fortunately, the way I wrote this was purposeful. It's kind of already set up. Remember that if you wanted to kind of take the A cross B, this would be I, this would be J, this would be K. You could put the bars around it if you want to just to make it easier, but cross product, eliminating the I row and column first, you're going to get 0 minus delta y times f sub x delta x. And I'm just going to write that as minus f sub x delta y. Instead, I'm just going to write it in order. Eliminating the j row and column, you're going to get f sub y delta x delta y minus 0. But don't forget you have to change the sign. So it's negative f sub y delta x delta y. And then eliminating the k row and column, you're just going to get delta x delta y minus 0. So you get delta x delta y. So that's our cross product. But we still need the magnitude according to this because we're trying to find the areas of these parallelograms, the areas of each one of these patches. So I'm going to have to take the cross and then take the magnitude. So the magnitude, remember the magnitude is going to be the square of each individual piece added together and then take the square root. So we're going to have a big square root here. Hopefully I can fit this in. We'll see. I'm going to take the square of the first piece, add it to the square of the second piece. The good thing about this, of course, is that those negative signs are going to go away. And then add it to the square of the third piece. Oops, delta y. All right, I'm definitely going to need a little bit more room, I think, so I'll have to drop below on this one here. Magnitude A cross B. Distributing the square. The negative fx squared is just going to be fx squared. Then we're going to have delta x squared. My notation is not good. Squared, because technically I should have parentheses around each one of those, but hopefully you know it's not the x and the y that are squared, it's the entire thing, just for purposes of this proof anyway. Then we'll have fy squared, delta x squared, delta y squared, and then delta x squared, delta y squared. And hopefully what you can see there is that I have a delta x and a delta y both squared in each term. I can factor those out, and then I can take them out of the square root as a delta x delta y. So ultimately, the magnitude of A cross B is going to be, let's see, if I take the delta x delta y squared out of each term, I'm going to get a 1 here. I'm just going to be left with an fy squared, and I'm going to be left with an fx squared. So writing it in a better order, it'll be 1 plus fx squared plus fy squared delta x delta y. And that, of course, is the area of one patch. If I want the area of the entire surface, I'm going to have to take the double integral, adding up all the patches, and then adding up all the rows. So we're going to have the double integral over our domain of the square root of 1 plus f sub x squared, f sub y squared, and then if we make these infinitely small, the delta x and delta y become dx and dy. And it doesn't really matter which order you put those in. It could be dy, dx. It depends on if you're going to do a type 1 or a type 2 integral, double integral. All right, I think that'll be plenty enough for this video. I'm going to come back and do a few examples, and then the last page, which is the surface area of a sphere, will be its own video. It's a bit longer to do. So I'll do the next 2 pages in the next video, and then the surface area of the sphere in the last video.